My name is Akshay Rajhans. I'm a research scientist at MathWorks, and I'm going to talk about our paper titled Specification and Runtime Verification of Temporal Assessments in Simulink. Let us take the case of cyber-physical systems, which are complex engineered systems that increasingly do sophisticated computation and close the control loop around a physical environment. Examples include smart devices such as smart speakers and doorbells and watches, to smart thermostats and smart robots and autonomous vehicles. Compared to the traditional development process where mistakes are often found late in the development cycle, the goal of model-based design is to create computational models which serve as executable specifications so that the mistakes can be found earlier in the development cycle. And then subsequently, automatic code generation turns that executable specification into auto-generated code that then can be deployed onto the hardware. Now, in order to show that our model satisfies the specification and does not have any mistakes, we need to reconcile the behaviors that our model exhibits versus those that are allowed by the specification. So on the top, we see a particular behavior executed by this model shown on the left. And on the bottom, we see maybe a couple of examples of behaviors that are allowed by this specification on the left. In order to be able to show that the behaviors that are possibly exhibited by the model are contained inside the behaviors that are allowed by the specification, it is important that the specification be precise and unambiguous. Indeed, the use of formal specifications in languages such as various temporal logics has been successful in the research community. And on the right, we see a concrete example of a mistake found in a lookup table in a automotive control model. And there has also been, recent development of various tool supports, namely Breach, Estolero, AMT 2.0, to name a few, and even more. But at the same time, temporal logics are hard to understand for non-researchers, i.e. the practitioners. On the left, we see this point being made by Joe Deshmukh when he was at Toyota, when he gave this keynote at HSCC 2015. And other researchers such as James Kapinski and Jens Eulerke from Toyota and Bosch have also made a similar point in the HSCC ICCPS 2018 panel and followed by this position paper on the right. So that is when this feature that we present in this paper comes in. It combines the best of both worlds. That is the intuitiveness of a natural English-like sentence with formal and precise semantics of a logical formula. Let us start with some preliminaries. A precise introduction to how Simulink operates and its semantics are beyond the scope of this paper. But to be able to understand the content of this paper, let us look at the basic building blocks of what a graphical block diagram looks like in Simulink. The main components are blocks, shown here circled in green, and signal lines that connect the various ports of these blocks with each other, shown here in blue. Now, this particular example is that of a bouncing ball whose dynamics are determined by the gravitational acceleration. And if you simply press the run button here on the model, then it'll simulate the dynamic behavior of this particular system over time and plot the position and velocity over time as shown in the right. For more information on how Simulink works, please refer to other resources on MathWorks website, such as the Simulink on-ramp. Let us now see a quick demo of this feature in action. we can head over to our MATLAB command window and type SL test mgr to launch Simulink Test Manager. This screen is where we'll define our new logical and temporal assessments. Under this section called System Under Test, let us specify the System Under Test model, which in this case is the bouncing ball model from the Simulink examples. I happen to have it open in the background, so I'll just say use current model, but I could have just as well typed it out or explored through my browser window. Now that I have that model, I'm going to switch over to this little section called Logical and Temporal Assessments. And here I'll say Add Assessment, which will give me three different types of templates. One is bounce check, the second one is a custom formula, and the third one is trigger response. Let's go ahead and add a bounce check example specification from the paper, which is to say that the ball position is always non-negative. So here it says at any point of time, and then we can select the bounce check pattern here, which is less than, greater than, inside bounds or outside bounds. Let's select always greater than, and the signal in this case is our bouncing ball position. So we can say ball position, and then the lower bound type is, or rather the lower bound value is, we can say position underscore LV, and the bound type is, we can select greater than or equal to. And then we see here that the two symbols that we just introduced, namely ball position and position lower bound, are unresolved. So that's why we get this red exclamation mark. So we can click on this and say map to model element. In this case, we want to map ball position to this particular signal on our model. So that is done. Now this is resolved. And the other one we can resolve to expression, and we can just say 0. But this could be something that varies over time as well. So here, for our benefit, what we just specified in terms of this structured template has been graphically illustrated as a sample fictitious trace that will satisfy this specification. And we can, generate other examples of passing specifications as well as failing specifications by exploring patterns, like here. So we can generate new examples like this, and then instead of passing, we can select failing examples as well, where some trace might fail this this specification, and as well as select dynamic bounds when the bound itself varies over time, and again select passing or failing. Let's now specify the other assessment example from the paper. That one is of the type trigger response, and it represents the requirement that whenever the ball bounces, then within a little bit of a time period window epsilon1, the ball bounces back and stays above ground for at least another different time window tau. So let's see how to model that. So the trigger here is, so whenever something becomes true, and what becomes true, the condition is ball position equals 0. So that's something that becomes true. Then within a delay of at most epsilon1, and this is a variable again that we can specify a value to. And the response here is that something becomes true and must stay true for at least some time period. So in that case, the condition that needs to become true and stay true for at least that period is that ball velocity is greater than 0, and the time duration that it needs to stay true for is, we can call it tau. Now these new unresolved symbols we can resolve by mapping to either expressions to or to corresponding model elements. This one we can just give it a value, and we can change it later. 0.01, and ball velocity, let's map it to model element and this particular signal here. Uh, and then lastly, tau, we can again map to expression. And we can call this, say, 0.02. So now that we have our two assessments entered through this UI, we can now iteratively fold the expressions, and you'll notice that they start looking more and more like English language specifications. Uh, so here, let me just fold it, and then it reads like a sentence. For example, at any point of time, if ball position equals 0 becomes true, then with a delay of at most epsilon 1 seconds, ball velocity greater than 0 must stay true for at least tau seconds. Similarly for this specification. So this is what provides the best of both worlds. This is both intuitive and readable like an English language sentence, but also has behind the scenes a valid and precise temporal formula. So let us now see the assessment workflow. We have these two specified tests that we have just authored, and we can just say run, and then that triggers the simulation of the system under test model. The first time it runs, it's going to compile the model and simulate it. And we'll see that our test case failed. So let us now explore what is it exactly that failed and how to gain useful information from what we observed. So we can expand the two test assessments we authored. The position always non-negative seems to have passed. So we can expand the expression tree and see what exactly happened. So this is the position curve, and it does stay always non-negative, and that's why this condition evaluates to true, and the ultimate assessment passes. Let's now head over to the other one, which is non-chattering. And here we see that the expected behavior is not satisfied, and we can iteratively expand the different assessment expression trees and see what exactly happened. Uh, so here is, so basically in the initial few bounces, the ball does come back up and stay up for the specified duration. But towards the end, we see that it's not really staying up for how long we want it to stay up for. So we can expand on the time period and see that it is indeed not staying up for the period that we asked it to stay up for. And here is an explanation of the failure in words for a particular instance. In this case, at time 20.18397, basically the ball velocity was expected to be greater than 0 for at least 0.2 seconds, but that did not turn out to be the case. And then we can go navigate back and forth between various failure points. So here are other failure points in time. So at those corresponding times also, the specification is not satisfied. So in summary, we saw the temporal assessments feature from Simulink Test that combines the best of both worlds in terms of formal, precise semantics of logical formulas, but they can be read like English language sentences, making them more intuitive for engineers and practitioners. We saw that there are templates for bounce check, custom formula, and trigger response patterns that are often found in practice. We also saw that there is graphical help for fictitious pass-fail test scenarios during authoring time for a given specification, as well as graphical and textual help for pass-fail test results during assessment time or simulation time. And lastly, we saw expression trees that can help us narrow down our failures in subformulas as well as subparts of the model, which is the system under test model. I cannot wait for you to give it a try and look forward to hearing from you. Thank you.